Hello, my name is Charity Garland and I'm with Berkeley Air Monitoring Group, and I'll be talking to you today about the methodology for estimating and verifying ADALYs from exposure to cleaner household air. We'll be talking about personal exposure monitoring, which is the foundation for the ADALY methodology, and the results that come from the ADALY methodology using the 90-30 precision assessment. We'll talk a little bit about the guidance for field testing methods, CO monitoring, and when it's appropriate or required, as well as the information required for the HAPIT model. The ADALY methodology uses exposure to PM 2.5 as the indicator of health. And this is a better indicator than household air pollution, as it's the direct measure of a person's exposure to PM 2.5 rather than measuring just the source of exposure, being the kitchen. And we all know that PM 2.5 leads to negative health impacts such as cardiovascular disease, respiratory disease, and lung cancer. And these understandings of the negative health impacts are what allow us to model the overall improvements in health due to a project technology. The PM 2.5 is the dominant contributor to the burden of disease from air pollution, no matter what the source. And so that's why PM 2.5 is being measured and used as the main indicator for health. Personal exposure monitoring, or PEM, is the measure of an individual's exposure to a specific air pollutant. In our case, we're looking at PM 2.5, but this could also be the personal exposure of carbon monoxide or ozone or other things that are pollutants that people are exposed to. This methodology focuses on exposure to air pollution in the form of PM 2.5 and is largely driven by PM 2.5 concentrations in the kitchen. However, kitchen concentrations are not great indicators of actual exposure levels because of the variable other sources of PM 2.5 that a person is exposed to throughout the day. Personal exposure is the average concentration of any sort of pollutant that a person is exposed to over a specific time period. So in our case, PM 2.5, but this can also be any other pollutant. And it accounts for their movements throughout their day. So being in their home, going to work, sleeping, any of the different microenvironments that they're exposed to contribute to the overall average personal exposure. And the methodology sets forth a technique for characterizing this exposure from residential fuel combustion as the main source, but all other sources are also contributors. And it's not necessarily correlated directly with indoor concentrations because there's so many different contributors to personal exposure throughout a person's day. So we see time and again that there's not a direct correlation, and so that's the reason that we measure exposure directly. Human activity follows a diurnal pattern, meaning lower concentrations at night and higher concentrations during the day typically. And so because we see this variability, exposure should be monitored continuously for at least 48 hours. And it can be monitored for longer if more data is of interest. However, it should always be in 24-hour increments. So 48 hours plus an additional 24 hours, but it should never be an additional 12 hours because you would capture that full diurnal pattern without doing a full 24-hour additional measurement. The exposure measurements should always meet the 90-30 precision rule, and we'll talk a little bit more about that in future slides. So there's two scenarios that will be measured. There's a baseline scenario, which consists of the baseline exposure before the project technology is in use. So while using the traditional or original cooking technology. The exposure measurements are required in at least 30 households at a minimum in the target population, so wherever the project stove is being disseminated. And the measurements of PEM in the baseline scenario must meet the 90-30 rule. The samples should be conducted on the primary cook for 48 continuous hours. They should be conducted in the season that's most representative of the full year. So for example, if 10 out of 12 months are rainy, then it's better to conduct the measurements in the rainy season versus the dry season, even though it might be logistically preferable to take the measurements in the dry season. And households where the main cook smokes, or which are not representative of the community at large, should be excluded. In the project scenario monitoring, it's very similar to the baseline scenario monitoring in terms of the tools and the methods. However, when we're thinking about our sample size calculation and our recruitment, we need to consider the likelihood of participant dropout or exclusion. So increasing the sample size in a way that will account for this dropout is useful, especially in before and after monitoring, where the duration of monitoring is so much longer than in cross-sectional studies. It's important that the target households for the project scenario are still using the project technology, and that's something that will be discussed in Module 2 on usage monitoring for how to determine that. Just as the baseline scenario, the exposure measurement should be carried out for a minimum of 48 hours in each household. And also, just like the baseline scenario, if light scattering measurements are being used, they need to be adjusted based on gravimetric equivalent concentrations. Personal exposure can be measured using either gravimetric or optical methods, and I'll go into detail about these two different methods in the next several slides. But the gravimetric method is the gold standard, and optical methods need to be adjusted by gravimetric coefficients to get gravimetric equivalent optical measurements. Gravimetric monitoring is the gold standard for PM measurements. It's a direct measure rather than an indirect measure such as optical measurements. It's more accurate than optical measurements, and so is always recommended in at least a subset of the measurements being made during PEM. Just briefly, gravimetric monitoring consists of a pump that draws air through a cyclone, which is shown here, this metal object. And a cyclone uses particle physics along with a very precisely set flow rate to remove particles that are larger than 2.5 micrometers. The particles that are smaller than 2.5 micrometers or equal to 2.5 microns are deposited onto a filter. And this filter has been pre-weighed. So it was weighed prior to sampling, and then it will be weighed again after sampling. And the difference in the mass of the pre-sampling weight and the post-sampling weight is the mass deposition of the PM on the filter. Filter contamination can be an issue, so that we use something called field blanks to correct for any changes in filter mass unrelated to the sampling. So handling, transport, contamination, things like that that might affect that mass difference between pre and post weight that's unrelated to the actual PM deposition during sampling. The particle mass is then divided by the total volume of air sampled, and the volume is known because you have a very precisely set flow rate in terms of volume per unit time, and then you time the sample so you can calculate the total volume of air that passes through the filter. And the particle mass over the volume of air yields the particle mass concentration in units of micrograms per meter cubed, and that's the average over the entire sample period. The gravimetric measurement, while it's the most accurate, it's fairly expensive to obtain the equipment, use a controlled laboratory for filter weighing, and requires some burdensome equipment worn by study participants. So there's both pros and cons to gravimetric. Light scattering PEM estimates are based on the amount of light that's scattered by the smoke particles inside of a sensing chamber. And a sensing chamber example is shown here. The smoke enters and exits through a diffuser, and there's an LED that pulses light shot at that sensing chamber. So So when there's no smoke present, the light shoots directly through and isn't detected. Now, when there's smoke in that sensing chamber, it's scattered off of those particles, and light that's scattered is detected by the photodetector that's set at an angle from the LED. And the amount of light detected is proportional to the amount of smoke in the sensing chamber. And because of this continuous measurement, it allows for minute-by-minute concentrations to be recorded. That said, there are typically high or low biases that are observed with this kind of light scattering device because of differences in particle size, shape, color, etc. And so because of that, a co-located subset of gravimetric and light scattering measurements are recommended so that a coefficient can be applied to optical measurements to yield a gravimetrically equivalent concentration of PEM. There are a range of instruments that can be used for PEM, and they vary from inexpensive to quite expensive, depending on what kind of technology you're using. The lower cost instruments are the optical light scattering instruments such as the PATS Plus, developed by Berkeley Air. A mid-range instrument would be shown here, the gravimetric pump and filter system, which is a SKC pump with SKC cyclone. And then on the more expensive side is something shown here, like the RTI's microPEMs, which has both a light scattering sensor as well as an internal pump and filter and cyclone type system. Here are a few examples of pumps that can be used with cyclones or impactors in a pump and filter setup for gravimetric PM analysis. Here is the SKC AirCheck 5000 that you saw on the last slide. It's also a Casella Apex pump and an SKC Airlight pump. Some examples of particle separators are shown here. The SKC Personal Modular Impactor, or PMI, is one method for separating out PM 2.5 from larger particles. The triplex cyclone by SKC, shown in the middle, and then again the RTI microPEM is an integrated system that has both a pump and a filter and a particle separator, all contained within this small unit. Now we'll move on to talk a little bit about PEM results analysis and how to assess the quality of the data. The 90-30 precision rule is a statistical concept the gold standard uses for assessing data quality. And there's worksheets for helping automate this assessment that the gold standard provides, which I'll describe in later slides, but I just want to describe the underlying theory behind the 90-30 rule so we understand it when using our worksheets. A minimum sample size of 30 samples is required for both the baseline and project scenarios. Of those 30 samples, if you look at the distribution, you can look at a specific 90% confidence interval for that data set. And the 90% confidence interval here is defined by these black dotted lines. And the 30% in the 90-30 rule designates a 30% change from the mean. So the mean minus 30% is shown on the left, and the mean plus 30% is shown on the right. And the 90-30 rule means that the 90% confidence intervals, those endpoints, should lie within plus or minus 30% of the mean. So if the 90% confidence interval is wider than 30%, so say it's the mean minus 40% to the mean plus 40%, that means you have a wider curve or more variability in the measurement, and so you have less confidence in your measurement, thereby not meeting the 90-30 rule. So just to help visualize what that 90-30 rule means, there's a little demonstration there for you. And if the 90-30 statistical precision is not met in the baseline or in the baseline PEM, then the mean PEM value needs to be conservatively adjusted with a two-sided lower bound of the error. So that means if the baseline doesn't meet the 90/30, you have to use the lowest baseline measurement. Now, for the project scenario, if the 90/30 isn't met, then you use the upper bound of the error. So you use the highest value of the project scenario measurement. And this will be described further in the following discussion of the worksheets. So here is that shows the sample size calculation for meeting the 90/30 precision rule for PEM. And this is for both paired, meaning before and after study design, so the same participants before and after receiving the project technology, or unpaired design, or cross-sectional, where there's two separate groups that are well matched but are not the same participants for baseline and project. And so looking at the calculation for 90/30, so this is shown here in this bolded column. If you look at the COV associated with your sample, so COV being the standard deviation over the mean, which is a measure of variability, and typically we see variability between maybe 0.5 to 1.1 or 1.2. And then we come over here and look at our sample sizes. So conservatively, our sample size of 30 minimum expects a COV of about 1. And should you expect to have a higher COV, you can increase your sample size accordingly. Here's a quick look at the worksheets I mentioned before. It allows us to copy and paste in our 48-hour exposures, our 24-hour average exposure to PM 2.5 for our baseline and project scenarios. And then it gives us this output that gives us the mean, standard deviation, coefficient of variability, upper and lower quartiles, interquartile range, outlier thresholds, and then finally it gives us our whether or not we meet our 90/30 rule. So it tells us what's the precision attained, and then does the result satisfy the 90/30 rule. Here this one says yes, and then in our project scenario it says no. And so it also calculates the what we should use as our PEM estimate. So in this case, it says use the mean, 218. In this case, it says use upper bound or increase sample size. And so the upper bound here says 75. Going on to some guidance for field testing. We'll discuss study design options now. So two commonly used methods are the cross-sectional study design and the before and after study design. And I talked a little bit about this during our sample size calculation slide, but we'll go into depth here. The cross-sectional study is independent samples or unpaired samples. So this means that the baseline and project sample groups are two independent but well-matched groups. So the baseline scenario is in homes that do not have the project stove, whereas the project scenario is in homes that have had the project stove for some time. Now, these two samples can happen simultaneously as they're in separate households with separate participants. Before and after study designs are paired samples. So the baseline measurement is made prior to the project stove dissemination. The stove is then disseminated, there is an adjustment period, and then the project measurements are made in those same households at a later date. So these happen in two different time points in the same households, whereas cross-sectional happens at the same time in different households. Looking at benefits and challenges of cross-sectional versus before and after, we can see that in the cross-sectional group, there's the least amount of planning needed since they can all the samples can be done at the same time. And they can be conducted during a single field campaign without requiring follow-up of study households at a later time, which is nice because it reduces the amount of participant dropout, the amount of field team dropout, and changes in things like weather or food or fuel availability. Now, and challenges or drawbacks are that the user groups have to be very well matched to ensure comparability. So there might be things that are unanticipated differences in the groups that make them hard to compare after making the measurements. So things like cooking location, fuel types, cooking behavior, socioeconomic level, availability, food availability or fuel availability, all of these things can make comparing two cross-sectional groups difficult. So some benefits of the before and after are that because they are the same people in the groups, they're directly comparable. Now there can still be some changes because of the difference in time. So if there's seasonal changes, if there's changes in fuel or food availability, those kinds of things can change over time and should be controlled for. But in terms of comparability and behavior and household type and things, much easier to compare with before and after studies. Some of the challenges of before and after designs are there's a greater burden on participants because of multiple visits required for baseline and follow-up, as well as changes in before and after monitoring, such as seasonal or availability of food and fuel, as mentioned before. The measurement length for the ADALY methodology PEM measurements requires 48 hours. So that can be either 48 continuous hours or be broken up into two 24-hour measurements separated by only enough time to switch equipment or filters or batteries. And the reason that it can be broken down this way is oftentimes equipment will not run for longer than, say, 30 hours. So we would need to be able to combine two 24-hour measurements to obtain a 48-hour PEM measurement. And whatever method is chosen should be implemented the same way throughout all of the monitoring campaigns. And one consideration would be to add an external battery to a device. Some devices allow that in order to extend battery life. Seasonal variability is a consideration, especially for before and after monitoring. So we should always conduct our monitoring in the most representative season. So for example, if we have many rainy months and fewer drier months, it's recommended to do monitoring in the rainy months. Follow-up measurements should always be done in the same season. This is especially important for before and after study designs because we want to be able to compare them directly to each other. And there's a longer period of adjustment in between the before and after measurements. So making sure those fall in the same period. In areas with really extreme climates and big climatic swings, the constraints imposed by weather should be taken into account. So things like accessibility in areas where roads are washed out, making sure to plan your study accordingly around these kinds of variables. Participant compliance is a very large challenge for personal exposure monitoring. Ensuring that your participant is comfortable and knows how to reach you if there's problems is really important. They should always be given clear instructions. So telling them that they're expected to wear it for 48 hours or using terminology that's better understood, so 2 days. And also telling them exactly what to do with the equipment during sleeping, bathing, and other activities when the equipment may get wet. And this might include explaining to them to hang the equipment next to their bed when sleeping, and even maybe installing a nail next to their bed to indicate exactly where to hang the vests. And of course, you should always ask for permission prior to hanging the nail in the household. And then emphasizing that the participants should never take off the equipment while they are in the kitchen and throughout the day, but especially in the kitchen and while cooking. Making sure that you have an appropriate exposure vest or some sort of harness for holding the exposure equipment will really enhance the compliance. So getting feedback from the participants, from the communities, from the women especially, on what they want to wear, what they're comfortable wearing, making it out of a material that's comfortable and attractive, using a design that is culturally appropriate. Those are all very important for increasing participant compliance. Here's a few examples of vests that were used in other studies. You can see they vary from backpacks with equipment on the straps and on the back to aprons with some pockets in the front, and then vests with pockets and some tubing that wraps around the vest itself. Incentivizing participation for exposure studies can really increase compliance and participation, but it's culturally specific and not always recommended in all locations. So in some locations, they can be seen as sort of bribes or create some jealousy and political unrest if certain members of the community are selected to participate and given a gift and others are not. So these should all be assessed on a study and location basis. In other locations, if no gift or sign of gratitude is shown, it can be seen as very disrespectful and can contribute to high rates of dropout. And regardless, gifts should generally be given at the end of the study to avoid unexpected consequences from the gift giving. But it should be suggested at the consent process whether or not they can expect some sort of compensation or gift. When planning a field study, there can be a lot of moving pieces, and it can be very complicated to coordinate with multiple different entities that are working together, potentially speaking different languages. So it's really recommended to draft daily household visits for each of the field teams, and also have lots of coordinating calls and check-ins during the field study planning and implementation to make sure that everyone's on the same page. There's a technical manual with detailed examples of some of the materials for helping plan these field studies. And it's also, recommended that data review happens regularly during field study implementation. We'll talk a little bit about CO monitoring. So CO measurements are only required for charcoal projects, so where charcoal project stoves are being used. And the CO is only placed in kitchens near the project stove, not on the person. So to hang a CO sensor, we've recommended to follow standard HAP measurement guidelines, which indicate that the best place is 1 meter from the edge of the cook stove, 1.5 meters above the floor, and at least 1 meter away from windows and doors. And this is very typical for indoor air pollution measurements in kitchens. It's important to mark the placement with a marker, which should be left in place for the duration of the study to ensure consistent placement during that visit, as well as potential follow-up visits for follow-up monitoring. If there's not a location that's 1 or more meters from doors and windows, the sensor can be placed as far from doors and windows as possible, but it's important to keep a record of how close the closest door and window is in the case that it's less than 1 meter away. Trying to keep equipment out of the way of rain or other sources where it might get wet is important. And installing a nail can be useful, but always ask the participant before putting a nail in their wall. And then other tools to help facilitate placement can include string wires, zip ties, bags, things like that. But it's always really important to pilot the the placement options before buying all of your equipment to make sure that your installation is appropriate. Some CO monitoring instruments that are available include diffusion tubes, which are shown on the left and are developed by SKC, and then LASCAR. And the diffusion tube is an integrated measurement, so it does sort of average PM over time, or average CO ppm over time, whereas LASCAR gives minute by minute measurements of CO. And now quickly just looking at what's required for the HAPIT model based on the PEM measurements. We'll be inputting the following information into HAPIT to run the model. So we select first the country or the state where the project is located. We enter both the baseline and project exposure measurements, the average exposure measurements, as well as the standard deviation. We look at the number of targeted households by the project technology, number of people per household, percentage of population using polluting fuels, the number of children per household under the age of 5, as well as the fraction of targeted households using the intervention. And the fraction of targeted households is defined based on a usage survey or continuous stove monitors. And that covers it for this presentation. Thank you for watching and enjoy the rest.